Okay, so welcome everybody. So today it's my pleasure to introduce our Bartoš from the Czech Academy of Sciences University. And he's going to talk to us about constructing compacta from relations between finite graphs.
Thank you very much, and thank you for giving me the opportunity to talk on this seminar. So first, let me point out that this is actually joint work in progress with Tristan and Ales Vignati. And then let me also tell you, okay, so this is a seminar, so please feel free to interrupt me anytime, and like if something is not clear and if I should define some term I'm using, just tell me, okay? Okay, so what's the big picture here? The idea is that we consider a certain construction which to every poset assign a certain compact space, which we call spectrum. And the intention, the idea here is that the element of this poset should correspond to certain basic open sets in this topological space. And ideally, the original order relation in the poset corresponds to containment of the induced set. We can also start we can like reverse the situation. We can start with the compact space X, take its open base, and then take its spectrum and asks, did we obtain the original space or not? So there is like this back and forth situation between these two constructions. So let me put here on the top of the board the notions we will be talking about. So we may have some compact space. There is a compact space X, and there will be a poset P, and we have this construction which turns poset into a compact space, this spectrum. We can also start with compact space and fix some bases. Yeah, and one concrete theorem, just for illustration here, is that, for example, every compact metrizable space can be reconstructed from a poset structure of any countable basis whose diameters go to 0. So take your favorite metrizable compact space, take any countable base whose diameters are going to 0 when ordered as a sequence, then forget everything about this base, just but the order of these sets, and then you are able to reconstruct the space back. Yes, and the posets here we will be interested in will often come from a sequence of finite graphs and some relations between the graphs. So we'll have yet another type of object, namely a sequence of graphs. And bonding relations. So this will be some sequence Gn and some relations. Yeah, and we can turn a sequence of such graphs and relations into a poset by stacking the levels on top of each other, just by taking the union. Okay, so how does it look like? So we have some graph G0, some graph G1, some graph G2, and so on. And between these two graphs, we consider some relation like this. And here we consider some relation like this, and so on. So the picture is like this. We have a graph G0, and inside we have the relation of the graph, the edge relation of the graph. Here we have G1, and inside we have the edge relation of the graph. But between these two graphs, we have this relation, this bonding relation below 0. Then we have yet another graph, and so on. And this pose set P is then just a disjoint union of these graphs. And the order relation on this pose set is just a reflexive transitive closure of the disjoint union of these relations here. And the idea, yes, okay, so these pose sets we obtain this way. They are called graded omega pose sets because they are like graded, and omega because you have omega many levels, and all these things are finite. And the idea, the intention here is that these edge relations in these graphs should correspond to when the corresponding basic open sets overlap if they have non-empty intersection. And when this happens, when we are in a situation that these overlaps, these edge relations really corresponds to overlaps of the sets, and the elements of the pose sets really corresponds to a subset of the space, like that faithfully represent the basis, then we can easily reason about topological properties of this space using this finitary structure of this thing, because we can see how exactly we have some very special basis in the space, and we exactly see how its sets overlap and how its sets are nested according to this picture. So so is this idea clear so far? This picture, how we stack things on together and how we get the pose set? Okay. So there is like very similar and more common approach to build compact spaces in such fashion, namely taking inverse sequences of graphs and then their quotients. So let me remind you that this inverse limit approach, this is something which is used, for example, in the context of projective Frey theory, which was introduced by Irwin and Solecki, and actually Frey theory was one of our motivations. Like to simplify, so I don't want to talk about Frey theory now, but the idea is that there is the Frey theory is about building some complicated homogeneous structures, and they can be built also in the context of topological structures using inverse sequences. And the inverse limit approach when building some spaces is also used by Dembski and Timchatin when they were building some topologically complete spaces, and the structures they were considering called cell structures. So let me remind you what is an inverse sequence and its limit. So inverse sequence is something like this. You have a sequence of finite graphs and maps preserving the edge relation, and the inverse limit is first the compact space, which is the inverse limit of the corresponding sequence of maps. Namely, you first take the product of these finite spaces, which is a compact Hausdorff space, and you take its subspace consisting of those threads which are compatible with the maps. This is the standard construction of an inverse limit. Moreover, since these are not just finite sets, these are graphs together with the edge relations, there is also the edge relation on the limiting structure. You can define that two points are adjacent in the limit graph if and only if all their projections are adjacent in the respective graphs. Yes, that's right. Our coding of graphs is that we assume that every vertex has a loop inside. So we are in particular allowed to contract edges into points, which is what is desirable here. Yes. So this relation is always closed, and it is always symmetric, and it is always reflexive, but it may not be transitive. But if for some reason it happens that it is transitive, then it is a nice equivalence relation, and we can just factor via this equivalence relation and obtain compact metrizable space this way. Because this G0 will typically be something like Cantor space, but this a special relation here will glue some pieces together and then can make you a nice compact space. Yes, so let me give you some kind of example or comparison between these two approaches. So typically it's not the case that if you would literally take the sequence and interpret it this way and do this thing with it, then this spectrum of the poset you'll obtain this way will be homeomorphic to the quotient of these inverse limits. Namely, because these posets typically don't see these edge relations in the situation when these are functions. However, you can make such a modification. You can, if you have a sequence like this, you can turn it into a modified sequence like this, and then the spectrum of the modified poset will be isomorphic. I didn't say yet what it is. So far, I'm just giving some ideas, some motivations, and at some point I will precisely define how this the spectrum is this construction which takes the poset into the space. But I haven't yet specified what exactly it is. Sorry?
But you might want to understand why you're not mistaken.
Not yet. I'll just show you a picture which illustrates some problems, and yeah, but at this point you don't see that it is so. Okay, so one concrete example of this. Suppose that you are building arc as an inverse limit the following way. Your graphs look like this. So you have paths of lengths to the n minus 2, minus 1. So these are your graphs in the sequence, and your functions just goes like this. So each point is split into two pieces, and so on. Yeah, so these levels are the graphs, and these are the functions here in the sequence Gn Fn. Okay. So if you consider this, then this G infinity, this inverse limit of the sequence is the Cantor space. And the equivalence you obtain here will be gluing the gaps. So G infinity is the Cantor space, which you can visualize here like the standard middle third. The standard middle third Cantor space. And these edge relations here, this relation here on the inverse limit will exactly glue these endpoints of these intervals together. Yeah, so this quotient of the inverse limit will give you the arc, the unit interval. But if you take just the spectrum of this poset, the poset doesn't see these edge relations here. They are not witnessed in any way by the poset structure. So the spectrum of this poset will be just the Cantor space itself, just the original Cantor space. It won't make the quotient. But if we perform this very concrete transformation of that, namely that instead of from the original graphs, we take sets of edges or isolated points. So here we would have just single one. Here we would just have this edge here. Here we have 3 edges, which will correspond to this. Here we have something like 7 edges. So this will be levels of our new poset. And now the order of this will come from refinement here. So this edge as this subset of the level is below this edge, because this point is below that point and this point is below that point. So this set refines that set, so it is below this. So in the end, the refinement relation of this will look something like this. Sorry. So this one is this one. This guy refines both this edge and that edge. This edge, which is a set consisting of these 2 points, refines this edge and also that edge. So this one will be actually below both of these. This one will be just here. This one will be below these 2 guys. And there should have been only 7 of them. So it will look something like that. And now somewhat, now like this thing somehow witnesses that there should be something like edge here. So now if we take this spectrum, which I haven't defined yet precisely of this space, we'll obtain again the arc. So this was more like comparison between the approach of quotients of inverse limits and the spectrum. So it is not only that, like using quotients of inverse limit, you can obtain every compact metrizable space. Using our construction, you can also obtain every compact metrizable space, but there is some kind of closer connection between the 2 things. Also, if you look at it here, these points here in this pose set corresponds to basic Klopen set of the Cantor space. And after we make the quotient, they will correspond to somewhat basic closed set. They will correspond to certain closed set in the arc. But here, these corresponding points will, by definition, by design, more correspond to open sets. So the intuition here is slightly shifted. Okay, so this was just to compare these 2 constructions to put it into context. But another thing is like why we are considering this construction. So one of the goals is that we want to present certain well-known spaces as Freise limits. And in this context, we mean Freise limit in the following sense. So we here put yet another kind of objects, namely a category of graphs and relational morphisms. Yes, some calligraphic C. Okay, let me make some space here. So we fix some particular class of finite graphs, some which we like for their shape, for example. These paths, something like this, graphs of that form, for example. And among them, as a morphisms, will be some co-bijective co-bijective relations. So now our morphisms, as here, as here, are not functions but relations. We are usually interested in some particular relations which we call co-bijective, which means that if we have this relation between some G and H, we want that it is some kind of generalization of a surjective function. So we want that it preserves the relation. So if two vertices are related by an edge in the domain graph, and this vertex is related to that vertex, and this vertex is related to that vertex, they should also be related by edge here. So the relation is preserving the edge relation. This is one thing. Then we want them to be co-bijective, meaning like generalized surjective function, preserving on one direction. Yes, like from domain to codomain, and here like this is domain and this is codomain. Yeah, sometimes. But regarding this co-bijectivity, we want like to be surjective on both sides. So for every guy here, there is some guy on the other side, and for every guy here, there is some guy on the other side. But moreover, there is this co-injectivity that it somehow generalizes being a function. Namely, for every guy in the codomain, there exists a guy in a domain which is connected to that, but such that this one is the only one to which this guy in the domain is connected. So this guy goes only to this one. Yeah, this may be also connected to some other guys, and this can be also connected to some more guys, but each guy here has one guy here which goes only to that one. So this was just like explanation or partial explanation for this word co-bijective here, this extra assumption. But aside that, we just take some graphs of some particular shape we are interested in, like paths, and maybe also some particular morphisms we are interested in, for example, monotone, something like that. And then in such category, we may try to prove that this is a that it contains graph of surjective function, like going that way. I guess so. Yes, like this part, it seems so, yes. Yeah, you would need to restrict from one on the other side. Yes. Yes, so we take our favorite category of graphs and relations between them, and if we prove that it is a Freyse category, namely that it is directed and has the amalgamation property, which I'm not defining here right now, then there will exist some very particular sequence of that form called Freyse sequence, some kind of very rich sequence that like absorbs, exhibits all the complicated behavior which appears in the category. And then this is some very interesting choice for this sequence here. So Freyse sequence. Yes, this is like a template for the thing. So we fix the category. We show that it is nice enough, so there exists a Freyse sequence. So we have this sequence. Then we consider the corresponding poset and its spectrum. And this will be the space, the Freyse limit we've built this way. What do you mean? Like any sequence in the category is Well, this was just like a definition of how morphisms look like in the category, because these are not morphisms in the category are not functions, like not graph homomorphisms, but rather these special relations preserving the function, the edge relation. Yes, so we get the nice sequence, we get the poset, we get the space, and if we also prove that some class of even nicer relations form something called wide ideal, it will turn out that this poset will be nice enough, it will be well behaved, and it will like faithfully represent the structure of the space. So namely, the point is that if we follow this template and we show that nice morphisms form a wide ideal, then it will turn out that this spectrum will be always Hausdorff space, that the poset will faithfully represent the basis. So the order relation of the poset will exactly correspond to the actual containment relation of the open sets in the space. And the edge relation in the graphs will exactly correspond to the overlap relation of the corresponding open sets here. So in the end, then we can like nicely reason about how this space looks like with respect to the original category we started with. So we know, yeah, our space has this very particular basis of that particular form where sets are overlapping exactly as we wanted, because we fixed this category as we wanted. And then from that we induce the topological properties of this space, and then identify, yeah, this is the pseudo arc, yeah, this is the Lelek fan. It is an ideal, which means that if you compose a map from it with any other map in the category, it is still there. And white in this context mean that from every object there leads one map like that, at least one map like that. Maybe I'll give more details later, but this was more just to give some basic ideas. And some examples of these complicated topological spaces, of these structures which are standardly presented as a phrase limit in the projective setting according to Irving and Soletsky. So some of them we were able to describe also this way, and to show you some examples regarding the choice of the category here, and the morphisms here, and then what will be the phrase limit here. If we take just all the discrete graphs, all the finite discrete graphs, and all the co-bijective morphisms, then in this case, they are exactly the same thing as surjective functions. Then as a spectrum, we obtain the Cantor space, like exactly this thing, which is no surprise, but it just like fits the picture. Sorry? Yes, in this context, in discrete graphs when there are no edges. Yes. If you take the category of all paths, things like that, and all monotone co-bijective morphisms, then you'll obtain the arc as the spectrum. On the other hand, if you take all co-bijective morphisms between the path, then you will recover the pseudo arc as a spectrum. And if we take all fans, which would be graphs, let's say, of this shape, that there is one common root node, the only node of degree greater than 2, and then some spikes from it, something like that. Then if you take something called root monotone and end preserving maps, then you obtain the Cantor fan. And if you take all root monotone maps, then we'll obtain Lelek fan as the thing. So if you heard something from continuum theory, maybe some of these spaces are familiar to you. This is more like for illustration of the theory. Yeah, but to take this with grain of salt, we are still like working on proof of some of these. There is still some details which need to be figured out. But this is some like representative table of standard spaces which can be constructed this way. Yes, like we are working with graphs, so it is somewhat natural that these spaces are one-dimensional. Menger curve was actually there in a previous version of this table. Like Menger curve, we believe that we would take connected graphs and monotone maps, but then we found out that there is maybe we are not so sure about this one that will obtain that one, so I removed it from the table, but it is on the list. It is like to be identified. The thing is that what was the concept of the problem was with amalgamation, right?
Yeah. Well, basically, I think we need some kind of combination volatility together.
Yes. Yes, the thing is that we want to prove the amalgamation property in the category, and now we are having a category where the morphisms are the relations, not just the functions. And sometimes there is a certain trick which allows us to conclude the amalgamation property of all these relational morphisms just from the amalgamation property of the corresponding functions. But in this case, it didn't work. So we still are looking like what would be the appropriate notion of slightly restricted class of graphs and morphisms when the amalgamation would work and which would correspond to the Menger curve. Yes, so again, like this was just overview, but it already took half an hour. So just quickly through this. So there are these graded omega pose sets. Actually, you can recover this sequence back sometimes when this is a graded omega pose set just by taking the levels. Yes, so there is this construction which takes a pose set into a compact space. And pose sets we are mostly interested in come from sequences of graph and relations. And sequences of graph and relations we are mostly interested are phrases, sequences, or certain categories of graph. But now finally let me to actually define what is this construction. This construction which takes a pose set and gives you a compact space. So in a classical point set topology, the situation is that you start with a set of points, and the topology gives you what are the open sets, and then you can also talk what are covers. So like the order here is first points, then open sets, and maybe then covers. But here the situation is somehow inverted. We rather start with abstract basic open sets with the pose sets. Then we define what are supposed to be covers, and only in the end we obtain a points as some kind of filter-like things. So the construction looks like this. So we start with some abstract basic open sets, and this is the pose set. Then we define what should be covers by these basic open sets. So first we define we use an order or the induced order relation on a subset of the pose set. We say that one subset is below other subset if for every B in B there exists C in C such that B is below C. So this is like the refinement order. B refines C if every element of B is below some element of C. Which direction? Like typically like a priori no, but usually it will be. Like for example, you could have just this Cantor tree which was not directed. Yeah, so we consider the refinement order on the subsets of the pose set. Then we say what it is like a basic abstract cover. We call it band. A band is a finite subset of the pose set, such that every element of the pose set is comparable to some element of our band. So this is the pose set, and band is something like this, some finitely many things, such that everything is either above or below some of them. So that's a band. And a cap, which is this idea of this abstract cover, is any subset which is refined by a band. So we take band as a like basic building blocks, and then abstract cover will be any set which is refined by this. Of course, if something is supposed to be a cover and it refines something else, then this other thing is cover, has to be a cover as well. So we define caps, and now finally we define what are points of our space. So by a selector, we mean a subset of the pose set which means every cap. It intersects every cap. And the spectrum, the set of our points, will be exactly the set of all minimal selectors. So points will be minimal selectors with respect to inclusion. So the smallest sets, minimal sets which intersect each cap. Note that every selector contains a minimal selector. This is because this condition of intersecting with every cap, it is enough to intersect every finite cap, because every cap has a finite subcap, because every cap is refined by a band which is by definition finite. This is where like compactness is inherently built in. What happened with the projector? Nothing, hopefully. Yes, so because of that, because these C's here can be finite, it is enough to consider finite C here. Every selector contains a minimal selector just by Zorn's lemma. And what is the topology on the space for every original? Sorry. Yes, like these C's can be considered finite. So if you have just like decreasing chains of these selectors, then if the intersection fails, it was already the failure was already on some level there. Yes, and like every element of a poset, this element P corresponds to this concrete set of points in our spectrum, literally just those selectors which contain that particular element of the poset. So this is like a concrete realization of this element of the poset. You can
the spectrum maybe
can there be no band completely? Maybe sometimes there is just one band, sometimes it is just a point, but can there be no band?
Nothing is confirmed.
Yes, so it can happen that spectrum can be empty.
Like to be a band.
Like if you have, you mean just this, like just infinitely many incomparable things.
Yeah, it's a band of the whole thing. Yeah, so the whole thing, but it's supposed to be finite.
Yeah, so
yeah, so you have to get logical, you have to restrict to these graded process and finite level. Then you know there's always at least one.
Yeah, so in principle it can happen, but it is like, so this is like an ugly representation of the empty space, because you can have just much nicer representation of the empty space taking just the empty poset, right? Yeah, so you can view it the way that the element, this is like a code for an open set, and this is the open set it induces in the poset. And so the spectrum is endowed with the topology generated by these sets. So this is the overview of the construction. So is it clear how it works, how it's defined, this particular construction? In a moment, I'll I'll give you some properties of it, and I'll also show some particular examples, like given this poset will obtain that, given that poset will obtain that, to give you just some intuition. Sorry? We don't know yet. I mean, we have some ideas of what should be morphisms between posets, which are appropriate, and they are indeed appropriate under some extra assumption, but we haven't figured out all the details of it. Like if we restrict, I believe that if we restrict to a suitable class of posets, then it could be made functorial, I think.
In general, you can get V to one. What do you think about how those spaces get?
If we provide appropriate definition of morphisms. Yes. So this is the construction. So summary of some very basic notions. If we start with absolutely any poset, we'll obtain a T1 compact space using this construction. Every minimal selector will be some upwards closed set in the poset. And this family of sets will be open subspaces of the set. This is just by definition. And moreover, we can there is often the situation that we have like some abstract phenomenon going on in the poset, and like its corresponding concrete phenomenon going on in the compact space. So for example, here about covers, you can take a subset of our poset and ask, is it an abstract cover? Namely, it is a cap. This is what it means to be abstract cover in our sense. Or you can also ask, okay, take the corresponding family of sets, of subsets, of open subsets in the spectrum and ask, is this an actual cover of the space? And here in this particular situation, they are coherent. A subset of the poset is a cap if and only if the corresponding set of open sets is a cover of the space. There will be more phenomena like this when you need some extra conditions to get correspondence. Okay, so now if it is not just a poset, if it is an omega poset, so something like this. Again, I didn't define omega poset precisely yet, but the poset of this form, the poset you obtain by stacking several finite things on top of each other. So if we are in a omega poset, then the spectrum is always second countable. Moreover, every two caps have a common refinement. And with that, it is closely connected that every minimal selectors will be not only a preset, but also a filter. So every two things in the selector, there will be something which is below both of them. And this canonical family is not only sub-basis, it will be basis. So this is where we get like this directedness. So omega posets are good for two reasons, because it makes your space second countable and because it makes your structure directed in a sense. And moreover, if we have a regular omega poset, which is again something I'll maybe define later, then we'll get that the spectrum is Hausdorff and so metrizable. Because by omega poset, we are also second countable. So we have a condition which will in the end make this space Hausdorff. Yes, so now some concrete examples. So I already mentioned that if as our poset we take this thing, the full binary tree, then we'll obtain the Cantor space as the spectrum, because these minimal selectors will exactly correspond to the branch to branches of this tree. If we take such a poset, and it will be easier to just draw a picture. So such a poset such a cum, this is like a canonical representation of a converging sequence, of a convergent sequence using our framework. You have as a minimal selectors, you have those induced by these atoms here, and then you have also this one corresponding to this branch here. So it exactly corresponds to a convergent sequence. And these points exactly correspond to these canonical open sets of the convergent sequence. To obtain something non-Hausdorff, just for illustration, if we glue two of these like this, if we have a poset like this, then this poset will give us the non-Hausdorff convergent sequence, like the convergent sequence with two different limits. Yeah, like this standard example of something what is not Hausdorff, because like these two guys corresponds to these two limits, and this corresponds to the isolated points. So this is some particular example of something non-Hausdorff. Yeah, so this whole thing, when we start with like abstract sets and then obtain points at some kind of filter like objects, this looks kind of like stone spaces, right? When you start with Boolean algebra and obtain the stone space. But this construction works differently. So for example, it doesn't like generalize it right away. Namely, I want to break a possible intuition that if you start with the Boolean algebra and you remove the bottom element and you take this as a poset and take its spectrum, it is like something different than the stone space. Namely, if you start with atomless Boolean algebra, then like everything collapses and you will get just a singleton. If you take atomless Boolean algebra, remove the bottom element, then the bands will be exactly finite subsets which contain the top element. So the only minimal selectors consist just of the top element, and there is just a single point. And one particle space which is not second countable, we can construct this would be 1-point compactification of a discrete space of any cardinality. Namely, if we do the same thing, but with a finite cofinite algebra of sets, of subsets of some cardinal kappa. So these are some of the examples. And now I can provide some more details on the constructions. So to formally define what is an omega poset, we can define a rank of an element in a poset in a transfinite way, like this. And an omega poset, and a poset is an omega poset if this rank is well defined and finite for every element in the poset. So maximal elements have rank 0, then stuff below that have rank 1, and so on. So omega poset means that this is well defined and finite, and also that every family of elements of bounded rank is finite. This is what does it mean to be an omega poset. Moreover, an omega poset is graded if it attains all the intermediate values of the ranks between 2 points, one below each other. So namely, what can happen is this picture. This is an omega poset, but it is not graded, because you have this point which is of grade of rank 0, you have this point which is of rank 2, but between there is no point of rank 1. So this is one kind of pathology which can happen in omega posets, and we don't want it, so we call those which are okay with that respect graded omega poset. Yes, because it is literally defined as a supremum. So it is like recursive definition. So it is. Like you don't have the choice. You always take the supreme. So what you want in the end is the idea is that if I take one point and look on all points which are strictly above me, they all should have strictly smaller rank than me. And I want to be best in this condition. So I want to have like the strict supremum of all these. So I take ranks of all these and +1 and supremum of that. But first I need to have defined these.
But can you always shift them all in?
What do you mean? You start with 0. Like if you have maximal element, you need a maximal element.
There's a maximal element.
There has to be, because otherwise you wouldn't have the definition. The definition wouldn't be like founded anywhere. So at some point you have an element which is maximal, so there is nothing above it. So we are taking empty supremum. So we'll take supremum of the empty set is in this case 0. It is the minimum. Supremum is the minimum element of the poset, whatever it is. And here the poset. No, but it doesn't happen yet. You take the supremum over empty set, so it's 0. So maximum elements have 0. Everything which has only maximum elements above it and nothing else has rank 1, and so on. So this guy has rank 2. Like regarding this guy, it could have just rank 1, but there is this guy which already has rank 1, so it has to have at least rank 2. So that's what it has. But graded means when this is also witnessed in between. So graded omega posets are exactly those which comes from these sequences of graphs and co-surjective relations. So if I start with something here, I'll obtain a graded omega poset there, and from that I can also recover the sequence back. So this is again the construction I was telling you about. So this is nice, some example of a graded omega poset, quite connected to this construction I've already. Omega. Omega reversed is an omega poset, yes. Omega itself not. So in this situation, when we are in a graded omega poset, we have that elements of rank nth are exactly those in the nth graph or set in this case, and the poset is atomless if this is not only surjective, not only co-surjective, but also surjective, whatever. But if we start with the order, we can like induce the edge structure on the graphs, saying that we put there an edge if it is like witnessed by something below, so that it like this is necessary to put these edges there if these are to be edge preserving maps. So for example, in this pose set, we can restore the edge structure like this. Yes, and then these relations will be preserving and reflecting. So there is some kind of correspondence. Like if we fix sufficiently nice bonding relations and sufficiently nice pose sets, then you can just decompose the pose sets into the levels and forget the remember into the levels with the edges, or put the levels back together. So then on these restricted thing, we would have like one-to-one correspondence here. So these were some details on omega pose sets. Yes, so now I have some more observations regarding how this part of the diagram works here, like reconstruction of the spaces. So you can start with a pose set, turn it into a spectrum in which the pose sets induces some basis, but then you can view this basis as a pose set, and then you can take again the spectrum of this pose set and ask if this is the same pose set as the original pose set, is the spectrum the same as the space, and what happens if you are going back and forth here. So if you start with a space and pick a basis, and then your new space will be the spectrum, you can ask when this natural map is a homeomorphism. If to every point you give the set of all sets which contains that point, which is like a candidate for a selector, when this is a homeomorphism. And then we have a theorem which says that this happens if and only if X is T1 and P is something called cap basis. So we have some condition on a basis of a topological space, which tells us when the space can be nicely reconstructed back. A cap basis is exactly what because if you take a family of sets, a basis of your topological space, then you can ask which of its subsets are actual covers and which of its subsets are caps from the point of view of the pose set. And if these two notions coincide, then we call it a cap basis, and then everything works. So we want that some subset covers X if and only if it is a cap. And in fact, the backward implication here always holds for T1 compact spaces. So only one inclusion needs to be verified in practice. So we have this nice notion of cap basis, which tells you that, yeah, this is the condition which describes where when starting with the space going to pose set and back works. But you can consider a similar situation. Sorry? No, you already need some assumptions for that. Yes. Or we can start with a pose set, take its spectrum, and take the realization of the pose set as a new pose set, and ask when this is an order isomorphism of these two pose sets. And again, we have a condition for that when this exactly happens, and we call such a pose set cap determined. And this can be defined by some condition talking only about possibly finite caps in the pose set. Namely, we want that whenever some element of the pose set is not below some other element, this is already witnessed by some cap, that there is some cap, some abstract cover, such that which contains this P. And if you remove it and instead put there a Q, it is not a cap. So this P was somewhat very essential in this cap. But maybe this condition is not that important. Like now, we just have a condition which exactly characterizes this situation. Yeah, and in fact, this condition characterizes only like reflecting of the order, preserving of the order is always true in this situation. Okay, so to put these things together, it turns out that every cap basis is a cap determined pose set. every cap-determined poset then gives a cap basis of its spectrum. But it can happen that you have a basis that is cap-determined poset, but it is not a cap basis. Because being a cap basis is not only property of the poset itself, but of the way how this poset lives in the space. So if you want to be a cap basis, it is really property of you need the right space there. And we have some example for that. These are some notions which I'll skip now. The point is that we have some practically verifiable conditions regarding this notion of being a cap-determined poset. And we also have a construction which will give you, for every second countable compact T1 space, a cap basis, which will be even like a nice cap basis, not only cap basis, which is already enough to reconstruct the space, but it will be a predetermined graded omega poset, some very nice poset. So as a corollary of that, we have that every second countable compact T1 space arises as a spectrum. You can obtain every second countable T1 space here by this construction, because you can always find a nice basis of such space which will reconstruct it back. Okay, and yet another concrete theorem on this relation, namely, if we are in a compact metrizable space and we have a basis of non-empty open subsets, then such basis is a cap basis if and omega poset, if and only if diameters are going to 0. So if diameters of these sets with respect to any fixed metric are going to 0, then this already guarantees that the basis will be a cap basis, and moreover that it will be an omega poset. And this is also a necessary condition. So some example, some picture like this. This is one particular cap basis in the arc. Yes, so the idea here is that we, for example, take the arc, and let's say we cut it uniformly into 4 pieces, and then we take every 2 consecutive pieces. This is one of the sets, this is another set, and this is yet another set. And we are doing this for every power of 2. We are cutting this in half and taking overlapping intervals of this form. Then we obtain a poset which looks like this, and this will be a cap basis. Of course, it is the diameters are going to 0 here, and this is one particular cap basis which will give you the arc in the limit. But right yesterday we considered the following modification of the example, namely, if we additionally put there these sets, so we also put there the union of this set together with this set, like going around. So if we additionally put these kinds of sets in the poset, then what we will obtain is a poset isomorphic to the following very nice poset, giving a similar construction for the circle. If you take a circle, in the complex plane, let's say, and you cut it into 2 to the n pieces like this, and then as you're covering open sets, you take these intervals which span like two consecutive elements of this division, like these kinds of things, then you'll obtain the same pattern, but circularly. So the pattern is always like this. We have some nodes here. There is one smaller which is below each of them, and there is also one which is below 2 consecutive ones. So we'll obtain such a pattern. In the arc, it goes like in an arc fashion. In a circle, it goes like in a circle way. And the poset here looks like this. But the point here is that this poset Q, consisting of these sets exactly, is a cap basis in the circle. So its spectrum is a circle, while P is still like a nice basis in the arc. This poset is a nice basis in the arc because we already started with the basis and we added some more sets on top of it. But this one is not cap basis of the arc because its spectrum is not the arc. It is the circle. We've just showed that the other poset, which is isomorphic to that one, gives you a circle. So you can have the very same poset realized in two different spaces, even though it is a very nice poset. It can realize a basis in two different spaces. Of course, only one of them can be the space it generates. Okay, so this was regarding the reconstruction of the spaces. Now let me just quickly give you a brief idea about regularity in this context. So a compact space, this compact space, the spectrum is Hausdorff if and only if it is regular, right? Because we are T1. So Hausdorff and regular in compact T1 spaces is the same thing. Recall that the topological space is regular if and only if for every point and an open set, there is some smaller open set which is in the bigger one contained even with the closure, right? And the idea here is that the relation, the closure containment, whether an open set is contained in a bigger one, even with closure, can be equivalently described using stars of cover. So this is there in the closure if and only if its neighborhood, it's blowing up by some cover, is contained there. The closure of an open set is in some other open set if and only if some star of this open set is there with respect to some open cover C. This is like the idea. Like in metric spaces, this compact set is contained, in metric space, if you have an open set with compact closure, it is contained in a bigger open set if and only if some epsilon neighborhood is contained there. This is like the same idea. But the point is that we can talk about covers and about stars abstractly in our framework. So this will in the end give us some nice conditions which we realize what is Hausdorff and what is compact. I have some details here, but since there is no time for that, let me skip that. We just naturally define what is a star in the abstract context, which describes the closure containment in the language of the posets. And then we say that a poset is regular if every cap is triangle refined by another cap. So something similar to, if you remember the axioms of uniform space, there is this star refinement notion that every cover is star refined by some other cover. So something similar here is what we call regular posets. And then if we are in a nice situation, this is exactly what characterizes regularity or Hausdorffness of the remaining space. Okay, so I had some more details on these maps, and on the conditions which will in the end assure that the resulting graphs and posets will faithfully represent the structure, the basis in the compact space. So there are some conditions, but no time for that. Yes, so maybe let me just quickly give you an overview of how this machinery works in the context of the pseudo-arc. So recall pseudo-arc is the unique chainable hereditary indecomposable continuum. Oh, there should be just two U's. So recall continuum is a non-degenerate connected compact space. Chainable means that every open cover can be refined by a chain cover, by a cover which looks like this. Two elements intersect if and only if they are adjacent in some enumeration. Hereditarily indecomposable means that every two incomparable subcontinua are disjoint. So situation like this cannot happen. Either the two continua are disjoint or one is contained in the other one. So for the pseudo arc, our choice of category here will be a category of paths, exactly these guys, and all co-bijective morphisms. We can then prove that this category is a Freise category, that it is directed and has the amalgamation property. Here, the amalgamation property, it is enough to prove it for functions, which is well known. And in fact, and we have also another proof of this fact, maybe a shorter one, which does not need to use Steinhaus chessboard theorem. So there is the amalgamation property. So this is nice. More so by the general theory, there is a Freise sequence. So Freise sequence namely means in these situations that we have a sequence like this, such that whenever we go out of the sequence, we can come back to the sequence. We have these relations between the graphs like this. And whenever someone gives us some other graph in our category and some relation like this, we can come back to the sequence. This is what Freise sequence means here. And we are able to show that for every path, there is even this nice morphism going into that path. In this situation, we would have something like, what is a nice in this situation? So for each of them, we will have some special below them, and then we need two more between them, which will be related to both of these. Like this morphism will be nice, in the sense that each guy here has multiple pre-images, but one of them is a pre-image which goes only to that guy. Every guy here goes somewhere. Anti-injective, star refining. Yes, and moreover, I put two guys here because now if I take, for example, this guy, not only that it goes below that one, but also if I take its star, he together with all the neighborhoods, there is one guy here such that all of them go below that. This is something which will give you regularity in the end. So by the general theory, we'll obtain a Freise sequence which will be consisting of nice morphisms. So then when we do this, when we obtain the poset from this sequence, stacking all the sets on top of each other and consider its spectrum, we can nicely reason about the resulting space. The sequence consists of nice morphisms, so the spectrum is a metrizable compact space. The poset faithfully represents its open basis, and these graphs faithfully represent basic open covers. Faithfully here means that there is an edge between two elements of the graph if and only if the corresponding open sets in the space intersect. Every open cover of the spectrum is refined by a basic open cover, and basic open covers are paths, so they exactly looks like this. They are chains, so right away we see that the result is a chainable continuum, just like this. And we can then also argue that the spectrum is hereditarily indecomposable, essentially just by, I have some steps here, but I think we don't have time for that. Essentially, you just takes fine enough cover and do some zigzag do some zigzag here, and this will directly give you that the compact space is hereditarily indecomposable. Okay, so to close up this thing, the idea of this and this machinery gives us some projective Freise limit as a spectra of graded omega posets coming from Freise sequences of some categories of graphs and bonding relations. But what I was not talking about, and what is a topic for further research maybe, is like, what about maps? And what about, for example, generic automorphisms? Like, can we represent not only spaces in these ways, but also maps between these spaces, like to code a continuous map between compact spaces by some morphism of the posets? And can this way we somehow see nicely a structure of, let's say, generic automorphism of the Freise limit, something along that line? And this is like the sketch. One related notion we've considered in this context is the notion of a refiner, which is like a candidate for this map between two pose sets. So we have one pose set, another pose set, and a refiner from P to Q would be some relation now between the two pose sets, such that every cap here is refined by a cap here. So for every cap here, there is a cap here, such that for every guy here, there is some guy there, such that this is below it during this relation. And just a sample theorem of this form, if we have two refiners going back and forth between the pose sets, such that the composition of the refiners one way will be coarser than the original order here, and the composition of the refiners the other way will be the composition there, will be coarser than the composition then the spectra will be homeomorphic. So this is something we're still working on. So that's all for me. Thank you very much.
Great, thank you very much for that talk. Any questions? Oh yeah. Well, I can reach you first. So
just a question. So an pose set we can express in categorical terms. Can you say what an omega pose set is in categorical terms?
What do you mean in the categorical terms exactly here? Oh, like in this sense. Oh. Like you would want to have something like yeah, so something like I don't know, but essentially take the definition of omega pose set, and so I guess you can define a rank in a similar way also in category, just talking about like non-identity morphisms, let's say. Or suppose that your category is not like pre-order, but like an order, so you don't have like loops in a category or something like that, and then you can talk about rank, I guess, and then you can apply the same definition maybe. But not sure how it will actually work. But some kind of rank may have some sense. Like if you want to somehow measure in your category, you have some kind of like not terminal, but like maximal objects, whatever, you can somehow measure like how far you need to go to get there. So then you could have some kind of something like that. But so in this context, it would correspond to something like we don't have just the information that this element is below that element, but also that if it is below that, it can be like below that in multiple ways that we remember, not that this includes there, but also remember some other information that we have like labeled inclusions by some extra information, which would turn it from a pose set to a category. But I don't know. This is just speculating.
Rather stupid question. Things like the pseudo-arc and the fan, I think they already had Frese limit realizations.
Yeah, they have. So they have Frese realizations in the other approach, in the approach of Irwin and Solecki. When you take again, like the situation is similar, but in their situation, you again take a category of nice graphs and nice morphisms, but their morphisms are always functions, not relation. This is one difference. Then they show that, yeah, this is a Frese class, so there is a Frese sequence. Again, think with the same definition, but then you take the limit in a different way. Instead of like building a pose set and from pose set getting a spectrum, they literally take the inverse limit and they'll obtain a topological space together with an equivalence relation, maybe equivalence relation. In this case, it will be equivalence relation. So their Frese limit will actually be the Cantor space together with some nice special equivalence relations gluing some points together. And only after you quotient by this equivalence relation, you will obtain the actual pseudo arc. And this way you can still obtain like they obtain the new characterization of the pseudo arc and realize it this way. This construction somehow tries to bypass the quotient part when you make the limit and then you do quotient, and gives you a way how to somewhat directly talk about subsets of the resulting space. So it is like a different presentation with the hope that maybe some things could be seen in an easier way using this approach.
Yeah, so I mean, yeah, a lot of these we're claiming we can just do it easier or better way, but we think this will also lead to actually new results as well. Like once you start looking at automorphisms, I think no one knows if there's a generic automorphism of the pseudo arc. Like all that has come very close, but we think she was hindered by the fact she was using this thing, whereas if you use our thing, we think it should be much easier.
So it has a separation, it's not a prime. When you perform one iteration of the objective. Yeah, so you have the separation P prime when you perform one iteration of going from poset to the compact space and then checking the basis. So is it the case that in general P double prime will not be equal to P prime?
You mean like at this?
We have some conditions which ensure that P prime will be isomorphic to P.
Yeah, you mean like on this slide when I was considering, yeah, like this thing, right?
Yeah.
So if you just start with some poset, get the space, and then get the basis in it, does this have to be a cap basis always? So you ask if like P prime is already always good. So
Yes,
if let's say if P prime is always cap determined. Not sure. Haven't thought about it this way. Is it this? Sorry?
There's definitely non-capitative poset.
Like in general, but like if you start with any poset, maybe not cap determined, then you realize it's spectrum, and inside you have the basis which came from them, and then you look on this basis as a poset itself.
Yeah, I mean, I guess it will be cap determined, but it's maybe a different poset.
Yeah, sure. It may be a different poset, but it will always be cap determined, this resulting poset, or can still this not be cap determined? Yeah.
I mean, I guess you know it's a cap basis. I think it should be a cap basis automatically. Of just by virtue of the way you constructed the thing, and then it should be captured. This might be a different process.
Okay, like I'm not sure, but it makes sense.
Okay, any questions?
Another stupid question. Oh, is there any chance that any of these SP, the topological spaces, like a topological manifold, as in isomorphic to Rn locally?
Like you can get any metrizable compact space this way. Not saying that it will give you some nice presentation of the space regarding some extra structure like manifold, but you can obtain any compact metrizable space, even every compact T1
So by going in this
using
process, going back, what is it, the fixed basis process, you can start with the topological manifold to go back and you'll get a poset.
Yes. You can always, if this is any compact T1, you can always find a poset which is very nice. So when you go here, you go back.
Yeah.
It is just stable right from the beginning.
So that, thank you. Yeah. Then I wonder, I mean, if the compact space you have is like a compact Riemannian manifold or something, what is the corresponding, what's the poset? Because you have like non-commutative differential structures and things like posets. It's a very out there question, but
You do have what? Some differential structures on posets?
Yeah, you can put them on graphs. I mean, you can calculate in graphs.
Okay, yeah, that would be interesting because I mean, we want to start looking at additional structures like automorphism, I mean homeomorphisms, things like that. And maybe you can also look at measures. Maybe you can also look at some kind of different differential structure. I don't know.
I have no idea if it's a good idea or not. It's just something that came into my head. So the Majid's book, there's a whole section, the new book. Yeah. Maybe something to discuss upstairs. All right, thanks.
Okay, well, if there's no more questions, then let's thank the speaker. I think that's it. Next week yet, I guess. No. Okay. Okay, so we'll leave that. But yep, thank you again. Thanks for coming.